So the previous example serves to give us the definition of the thing that we will call the Fourier series of a function f of x. So first we'll let f of x be defined for x between negative L over 2 and positive L over 2. Then the Fourier series of the function f of x is the trigonometric series a naught over 2 plus the summation from n equals 1 to infinity of an cosine of 2 pi n over L times x plus bn sine of 2 pi n over L x. Where the coefficients are the integrals, the definite integrals that we talked about before, a naught is 2 over L times the integral from negative L over 2 to positive L over 2 of f of x. An is 2 over L integral from negative L over 2 to positive L over 2 of f of x times cosine of 2 pi n over L times x, and bn is 2 over L times the integral from negative L over 2 to positive L over 2 of f of x times sine of 2 pi n over Lx dx. And what we'll see is that every trigonometric series satisfying reasonable convergence conditions is a Fourier series. And we'll denote Fourier series as Fs for short. And the reasonable convergence condition is particularly called the condition of uniform convergence. we'll get into what uniformly convergent means in the next lecture. But what we can do is go through and show relatively straightforward that if a given Fourier series or a given series is a Fourier series, then it'll be unique for a given function. And this can be made by noting that the functions involved in the Fourier series are all linearly independent from one another. So if you take two separate series, a0 over 2 plus the summation from n equals 1 to infinity of an cosine of 2 pi n over L plus bn sine of 2 pi n over L in the series is equal to times x in the series is equal to another Fourier series because of the linear independence of the functions cosine, sine, and the constant function 1. If two Fourier series are in fact equal to one another, you can use the linear independence of the basis functions. So on the left hand side we have a naught, on the right hand side we have a naught prime, an prime, and bn prime. And the linear independence of the basis functions imply that these coefficients have to be equal to one another because the corresponding infinite sums are convergent and converge to the same thing, which means that the infinite sum of a naught minus a naught prime over 2 plus the infinite sum from n equals 1 to infinity of an minus an prime cosine of 2 pi n over Lx plus bn minus bn prime sine of 2 pi n over Lx converges to 0, if these are two uniformly convergent series, and we subtract them, and therefore by linear independence of the basis functions, a naught has to equal a naught prime, an has to equal an prime, and bn has to equal bn prime for all n. We can also see that any Fourier series will be L periodic, so it has a period of L. And whenever these integrals have meaning, then we have this concept of a Fourier series for a given function f of x. So it's really the existence of the Fourier series is really dependent on what you get for the coefficients here. And this is the first condition that we'll put on f, and we'll investigate this a little bit more in detail in the next lecture. So we know that this will be true for continuous f of x. These integrals will always exist for continuous f of x. But what's important to point out is that this is also true for piecewise continuous f of x. So for instance, if you look for the Fourier series of the following function, that maybe looks like negative L over 2 to positive L over 2. And so there's maybe a discontinuity at C1, say, and the function looks like this up to C1, where then it jumps up to this point right here and continues on. It's this value right here, and then this value right here. So the Fourier series of such a function, which is piecewise continuous, will converge, end up converging, and it'll converge to something that looks like this. And a good question to ask is, well, what does the Fourier series converge to at the boundary points of this function? So this is what we're going to answer in the next couple of pages. That's the main thing here, is that so certainly the Fourier series exists, specifically the integrals for the Fourier series exist for continuous functions f, but it also exists not just for continuous functions f, but for piecewise continuous functions f of x. So this is a nice example here. And on this figure, right, the function itself will color in black in the corresponding Fourier series, and what it converges to I'll color in red right here. And you'll notice that I'm not coloring in these boundary points, the points where the function f is discontinuous, or specifically we have these points here that at negative L over 2, at C1, at positive L over 2, at C1 plus L, the period, so this point right here, and so on and so forth. We can ask, and these are the points of discontinuity of the function. And we can ask, what does the Fourier series converge to? At these points. And if you investigate this and you look at, say, plotting the Fourier series out in Desmos, or using the Python code that I'll provide for the class, for computing Fourier series, you'll see for any example that you do when you investigate that the Fourier series actually ends up converging to the average of the limit as you approach the discontinuity from the right and from the left. And this is exactly the general theorem that we'll end up having. So if C1, say, or we'll say if x star is an interior point of the interval from negative L over 2 to positive L over 2, then the Fourier series converges to the average of the left-hand limit and the right-hand limit at x star, which is 1/2 the limit as x approaches x star from the left plus the limit as x approaches x star from the right. And we can actually use this as a definitive formula. And then the only other thing that we have to consider is what happens on the boundary discontinuity, if there's discontinuity on the boundary. And the idea here is that it's the same idea. So into the Fourier series so at the boundary points, on one period, the Fourier series converges to the average of the limit as x goes to negative L over 2 of f of x plus the limit as x goes to L over 2 of f of x. And I'm not going to go through and prove this, but the proof of this is in the book. So I will go through and do a specific example. Let's consider the square wave. So this will be f of x is the piecewise function 0 from negative pi to x to negative pi over 2, 1 from negative pi over 2 to pi over 2, and then 0 from pi over 2 to pi. Where the example can be done using a general L if you want to, or I'm just going to use pi because it simplifies a decent amount when you go through and do the Fourier series coefficient calculations. This is from negative pi to negative pi over 2. This function is going to be 0 on this interval, and then it's 1 from negative pi over 2 to positive pi over 2. And then it's 0 from pi over 2 to positive pi. To positive pi. And when we go through and compute the Fourier series coefficients here, we have that A naught will be 2 over L integral from negative L over 2 to positive L over 2 of our function f of x dx. And the period here is 2 pi, so L is equal to 2 pi. Which then means that this will be 2 over 2 pi, or 1 over pi, times the integral from negative pi to positive pi of f of x dx. And the function f of x is 0, except for on the interval from negative pi over 2 to positive pi over 2. This will be 1 over pi integral from negative pi over 2 to positive pi over 2 of 1 dx. Which is just equal to 1 over pi times x from pi over 2 to negative pi over 2, which is equal to 1. And similarly for an and bn, an will end up giving you the integral from 1 over pi integral from negative pi over 2 to positive pi over 2 of cosine of nx dx. Because remember, when you plug in, if L is 2 pi, then 2 over L, like right here, is 1 over pi, and 2 pi n over L is just going to be n. And this integral ends up being sine of nx over n pi from negative pi over 2 to positive pi over 2, which is 2 over n pi times sine of n pi over 2. Which is actually equal to a piecewise function. It's negative 2 over n pi when n is 3, 7, 11, 15. It's positive 2 over n pi when n is 1, 5, 9, 13, so on and so forth. And it's 0 when n is even. for bn, you end up getting that the integral is 0 when you go through and do the evaluate the integrals. So it's important for you to check this for all n. Right. So for you to be able to justify why you get 0 for the bn integral. What that means then is that the Fourier series for the square wave I should say for this square wave is 1/2 plus 2 over pi cosine of x minus 2 over 3 pi cosine of 3x plus 2 over 5 pi cosine of 5x, and so on and so forth all the way to infinity. So you can re-express this a little bit nicer as 1/2 plus 2 over pi times the summation from k equals 1 to infinity of 1 over n oscillating between positive 1 and negative 1 for all odd values. This will be negative 1 to the k minus 1 over 2k minus 1 times cosine of 2k minus 1 times x. Because for all different values of k, 2k minus 1 is going to give you the odd values. So for k equals 1, you get 2 times 2 is 2, minus 1 is 1. For k equals 2, you get 2 times 2 is 4, minus 1 is 3, and so on and so forth. So for k equals 3, you get 2 times 3 is 6, minus 1 is 5. And likewise, negative 1 to the k minus 1, and k is 1, you get negative 1 to the 0, which is positive 1. And k is 2, you get negative 1 to the 1, which is negative 1, positive 1, and so on and so forth. So this is matching this right here perfectly. And this series is the correct Fourier series for this square wave example. One of the important concepts that we'll talk about is we talk about the partial sums, which right here I'll denote P. So if the Fourier series is P of x, we'll call it f of x, capital F of x. The nth partial sum of the Fourier series is going to be a naught over 2 plus the summation from k equals 1 to n of an cosine of 2n pi, 2 pi n over Lx plus bn sine of 2 pi n over Lx. So the zeroth sum is just the a naught over 2 term. The first partial sum is the sum of the cosine terms, the sine terms plus the first partial sum, or the zeroth partial sum, and so on and so forth. And so one of the big ideas is that the way that we're going to define convergence of a Fourier series is using the limit of the sequence of partial sums, partial sum functions, which is very, 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 very neat. But it'd be a good idea to go on to, say, Desmos or something and kind of graph for this function the partial sums, show that they are definitively converging to this function right here. So the next topic that I want to talk about is called odd and even extensions of a function. And this is for if we have a function defined on just a positive interval from, say, 0 to c. And we have two such extensions that we can give a given function. So suppose that f of x is defined on the interval from 0 to c for some positive real number c. We say that the even extension of f of x to the interval from negative c to 0 is the function, right, and the unique even function that matches f of x on the interval from 0 to c. So remember that an even function is a function that is symmetric across the y-axis. And so this is what the even extension of f of x look like. Sometimes I'll call this f even of x to denote exactly what it is. And so the concept of an even function was hopefully gone over in your Calculus 2 class. If not, if you don't remember it, that's fine. The only thing is that you just need to remember the exact mathematical definition of what it means to be an even function is that f even of negative x is equal to positive f even of x, which for the even extension then means that this f even of negative x is going to be positive, right, f of x on the interval. If I take a point negative x right here, then the value of the function here has to match up with the value of the function here. And this has a number of different very important properties. For instance, if you're integrating, say, a function from negative a to positive a, the integral of an even function over a symmetric interval will always be 2 times the integral from 0 to a of this even function, which for us means it's going to be 2 times the integral from 0 to a of just f of x dx. And this is typically shown in an undergraduate calculus class, but it becomes very, very important to use when we're simplifying and calculating Fourier coefficients. So it's going to be very, very useful. Likewise, we have a corresponding definition of an odd function. And let's make some more space here so that we have a little bit more space. The odd extension of the function f of x defined on the interval from 0 to c, and I'll use the exact same picture right here. Is the unique odd function that matches the function f of x on the interval from 0 to c. And so remember that f odd of x, or an odd function, has that f odd of negative x is equal to negative f odd of x. Or right, what we have is that it has to, this function f odd has to match f of x on the interval that we're dealing with for negative values of x. So if you look at, say, definition here, this is saying that f odd of negative x will be equal to negative f of x. And in pictures, what this amounts to is this function reflected around or about the y-axis, so geometrically, function will be reflected about the y-axis, and then subsequently reflected about the x-axis, to attain a function that looks like this, which is the odd extension of the function f of x. Definitely a different function than the even extension, with different properties. So you know that an odd function satisfies this property. which means that if you integrate an odd function from, say, negative a to a, because of the symmetry, like that this area right here will always be equal to this area right here, you'll always get a cancellation when you integrate this function, which will result in a zero value for the integral of an odd function over a symmetric interval. These are two very, very important simplification formulas when you're going through and calculating coefficients for Fourier series that are very, very useful. But not only that, we can take this idea of the odd extension and even extension of a function, and for a given function to find out an interval from 0 to c, actually use what we know about the Fourier series to come up with what are called the sine series and the cosine series of a given function f of x. So we say that the Fourier cosine series is the Fourier series of the even extension to the function f of x on the interval from 0 to c, and the Fourier sine series is the Fourier series of the odd extension to f of x on the interval from 0 to c. What does this mean? Well, it means that this function, we expect it for a series to converge to the function on this entire interval right here. And not only that, but we know the Fourier series will be periodic, so it'll converge to periodic repetitions of this function, the period of which will have the length of this interval. So the period here will be 2 times c. And when we go through and get our Fourier series coefficients, we get that a naught will be the integral, or 2 over L, times the integral from negative L over 2 to positive L over 2 of f of x dx. I should say of f even of x dx, which we know will be 1 over c times the integral from 0 to L over 2 times 2 and L over 2 is just C of f of x dx. The function itself on the originally defined interval from 0 to c. Likewise, an will end up being 2 over c times the integral from 0 to c of f of x times cosine of nx, or not nx, n over L times pi times x. And sine, the sine coefficients bn end up being 0, because the integral that you end up taking will be the integral of an even function times an odd function on a symmetric interval, which will end up being 0. So the Fourier cosine series, sometimes noted c of x, will be a0 over 2 plus the summation from n equals 1 to infinity of an times cosine of n pi over c x. Well, and this should not be L, this should be c right here. Because if L is 2 times c, then 2 over L is 1 over c. And 2n pi over L is equal to n pi over c. Likewise, the Fourier sine series, we have a slightly simpler series. I'll have that for the Fourier sine series. We still get, a repetition when we calculate this Fourier series, so the periodic function. But now, if you go through and do the Fourier series of such a function, you'll end up getting that Bn is 2 over L integral from negative L over 2 to L over 2 of f odd of x sine of n pi 2n pi over Lx dx. And on the interval from negative c to c here, we can integrate this as follows. So we know that this function for this function, we expect the Fourier series to converge to this infinitely periodic repeating function, just like the Fourier cosine series, with a period of L is equal to 2 times c. So if we go through and evaluate what the Fourier coefficients simplify to, the bn's are going to simplify to 2 over 2 times c integral integral from negative c to positive c of f odd of x times sine of n pi over c times x dx, which is just 1 over c. And one of the nice properties of an odd function is that if you take an odd function and you multiply it by another odd function, the resultant is going to be an even function. So this is the integral of an even function right here. So it'll be 2 times the integral from 0 to c of the function f of x times sine of n pi over c times x dx. So the Bn terms in the Fourier sine extension, or the Fourier sine series for f of x, are given by two over c times the integral from 0 to c of the function f of x times sine of n pi over c times x dx. And likewise, if you go through and calculate a naught, because f of x, or f odd of x is odd, is 2 over L integral from negative L over 2 to L over 2. Because f odd is an odd function, this integral will be 0. And likewise, the Fourier integral for an will be f odd of x times cosine of 2n pi over L times x dx. And an odd function times an even function is an odd function. So this integral will be 0 as well. So the Fourier sine series of the function f of x on the interval from 0 to c will be the sum from n equals 1 to infinity of bn times sine of n pi over c times x. So this is very cool, and it gives us two different ways that we can take a function on a positive interval from 0 to c and come up with a Fourier series that converges to the function on that interval, and off of the interval it converges to either an odd extension or an even extension, which is very neat. For different functions with different types of properties, we'll see that the cosine series is sometimes better to use, or the sine series is sometimes better to use, but they both have very, very neat applications and different convergence properties that depend on the properties of f. And the last thing that I want to talk about in this lecture, this introductory lecture on Fourier series, is what's called the complex form of the Fourier series. And this can be obtained by using what's called the Euler's formula. Which is a fundamental, probably one of the most fundamental formulas in mathematics. It says that e to the I times theta is cosine of theta plus I times sine of theta, where I is the square root of -1. It's a complex unit. But this can be proven using Taylor series in a Calculus 3 class. Typically I go over the proof of this. But the idea is that we want to take this and see how we can apply this to the Fourier series. And we know that in the Fourier series we have a term cosine of n pi times 2 over L x, and we have sine 2 n pi over L x. And so using Euler's formula, we can get that for any theta, cosine of theta is going to be e to the I theta plus e to the negative I theta over 2 and sine of theta will be e to the I theta minus e to the negative I theta over 2i, 2 times I. So these cosine and sine terms in the Fourier series expansion can be very nicely rewritten so that our Fourier series expansion is a naught over 2 plus the summation from n equals 1 to infinity of an cosine of 2n pi over Lx plus bn sine of 2n pi over Lx. This series is the same thing as a naught over 2 plus the summation from n equals 1 to infinity of an times e to the I times 2n pi over Lx plus e to the negative I 2n pi over Lx over 2 plus bn times e to the 2n pi over Lx minus e to the negative 2n pi over Lx over 2i. Which we can rewrite as the summation from n equals 1 to infinity of an plus bn over 2 for an plus I times bn over I divided by 2 times e to the 2n pi over Lx times I plus an minus bn over I divided by 2 times e to the I times 2n pi over L times x times -1. Which finally can be simplified to, we say C naught is A naught over 2 Cn is An plus Bn over I over 2, which is the same thing as An minus IBn over 2 when n is greater than or equal to 1. And then Cn is An minus Bn over I over 2, which is the same thing as An plus IBn over 2 when n is less than or equal to 1. The complex form of the Fourier series, f of x, can be expressed very, very simply as just the infinite summation from n equals -infinity to positive infinity of Cn times e to the I 2n pi over L times x. Which is a very remarkable formula and is fundamental in understanding where the formula for the Fourier transform comes in when we end up defining that. But this is a much nicer formula than this long expression for the Fourier series f of x. So this is going to be very, very useful to us. And it's nice to point out here, and I would go through and check this, that the Cn, each one of these Cn's, these coefficient Cn's, if you use the definition of An and Bn, right, each one of these coefficients for Cn is going to satisfy Cn is equal to 1 over L, where L is the period, times the integral from -L to L of the function f of x times e to the negative I times n times x. Negative I times 2n pi over L times x dx. So this would be a good thing to go through and check. But this is a very, very important formula, and we will find many, many, many uses for it. It's just another way to cast and write down a Fourier series. But thank you very much for tuning into lecture, and have a great day.